These aren't photographs. They're numbers. Calculated by a clever mathematical algorithm. It's called ray tracing. This simulation comes from the CUDA-based ray tracer we will build in this series. So, how does it work? Here's the 1-minute intuition. First, we model the world with triangles. Every shape, walls, spheres, even glass is approximated by countless tiny triangles. Next, we place you, yes you, at a single point in this 3D world. Then we draw a shape that contains everything you can see from that point. This shape, bounded by a near plane, that's your screen, and a far plane, that's the maximum distance we consider, is called a frustum. Next, we define a ray. A ray is just a line. Here, it is from your position, through a point on your screen, and out into the world. Now, consider this. We fire this ray from your position, through the screen and onward. If it intersects a triangle, we apply the laws of reflection, bouncing it to the next surface, and repeat until either it misses everything and intersects the sky, or it reaches the predefined bounce limit. If the ray eventually hits the sky, we gather all the colors from each bounce. The first bounce gets the most weight, the second bounce a bit less, and so on until we've averaged them into one final color. We then map that color back onto the pixel on your screen where the ray initially intersected. And because every screen has over 1 million pixels, we repeat this process for every single one. That's ray tracing, in essence. Now that we understand the big picture, let's start ridiculously small. We'll make a ray tracer that does just one thing. Produce an image file from math, a plain text.ppm file that shows a single shaded sphere. A ppm file is the simplest image format you can write by hand. The header has 3 lines, P3, meaning ASCII color values, then the width and the height, and finally the maximum color value, usually 255. After that, it's just red, green, and blue numbers for each pixel. In the end, we'll render something like this, a reflective sphere resting on a checkerboard plane. To get there, we first need to describe exactly how our ray tracer will function. That starts with one of the simplest but most universal mathematical objects in 3D programming, the vec3. The vec3 is a simple data structure that has 3 points, x, y, and z. Here we show a vec3 with coordinates 3, 2, and 4, and with an approximate length of 5. Using these 3 points, we can calculate useful information like the distance from x, y, z to the origin. Since this just returns a number square rooted for all inputs, we can square it to obtain an equally useful value. We do this because a square root function is notoriously slow. Here we define a simple C++ structure to contain our vec3 object. We also define simple operators for addition, multiplication, division, and subtraction for easy handling. These are useful utility functions that we use to find information about vec3s relative to other vec3s. These functions come from a high-level math field called linear algebra, which exits the scope of this series, but for now we can treat them as black box functions and understand generally what they do. The dot product is a value that generally describes how similar 2 vec3s are based on the angle formed between them. The cross product of 2 vec3s returns a new vec3 that is perpendicular to both input vectors. Its magnitude equals the area of the parallelogram spanned by the 2 input vectors. Its direction is determined by the right-hand rule. If you point your index finger along the first vector and your middle finger along the second, your thumb points in the direction of the result. The normalized function takes it in a single vec3 and then scales it down such that it only travels 1 unit of length. This is the set of all points that are a distance 1 from the origin, so every normalized vec3 lies on this sphere. Finally, the reflect function takes an input vector and returns a new vector that represents the reflection of that input about another reference vector. In geometric terms, it calculates how a direction would bounce off a surface whose orientation is defined by the reference vector, following the law of reflection. Earlier I mentioned that every single shape is built with triangles, but for our simple ray tracer, we are going to break that rule and build our scene with spheres instead. Here's a simple data structure to contain our spheres. Right now it contains information we can ignore for coloring, like albedo, metal, rough, speck, and shininess that we will worry about later. All we need to consider for now is the intersect function, and the vec3, the center, and the float, the radius. Now let's talk about ray-sphere intersection. Let the sphere be defined by a center C and a radius r. Let the ray be P of t equals O, which is the origin, plus t times d, where t is just some number greater than or equal to 0, and d is the ray's direction, which is often normalized. A point P lies on the sphere if the magnitude of P minus C squared equals r squared. If we substitute the ray's formula in for P, we obtain the equation r squared equals the magnitude of O plus TD minus C all squared. If we expand this equation and make it in terms of t, we find the quadratic a times t squared plus b times t plus little c equals 0. In this equation, a equals d's dot product with itself, b equals 2 times d's dot product with O times c, and little c equals O times c's dot product with itself minus r squared. The discriminant delta equal to b squared minus 4ac tells us exactly how many intersections occur. We can break this down into 3 distinct cases. Case 1. This is when the sphere is intersected twice by the ray, and this happens when the discriminant is greater than 0. Case 2. If the discriminant is equal to 0, then we know that the ray just grazes the circle and is tangent to it. Case 3. If the discriminant is less than 0, then the ray does not intersect the sphere anywhere. Now, if one of the first 2 cases occurs, we can go back to the quadratic we created and apply the quadratic formula to calculate the value of t at which the sphere is intersected. Finally, if we plug that value of t into p of t, then we have the exact point in space where the sphere is intersected. If the sphere is intersected twice, the larger value of t is ignored because it is behind the first value of t on the ray. I chose to do a sphere-based render before we created a triangle-based render because of the simplicity of the ray-sphere intersection function. It also has the added bonus of being much cheaper computationally than ray-triangle intersection. I recommend you attempt to implement the ray-sphere intersection function, but here's mine for reference. Now we add the floor. It is an infinite plane at y equals 0. A ray hits this plane the moment its y-coordinate becomes 0. Our ray is P of t equals O plus TD. So, on the y-axis, O sub y plus TD sub y equals 0. We solve for t. T equals negative O sub y divided by d sub y. If the ray is nearly parallel to the plane or the hit time is out of range, we ignore it. At a valid hit, the point P of t is where the ray intersects the plane, and the normal is just 0, 1, 0. For the checkerboard, we take the hit points, x and z, snap them to integers, and alternate colors on parity. There are no textures needed, the pattern just repeats forever. In both of the intersection functions we have programmed so far, I've used the hit class. The hit class is just a simple struct that contains a hit point, the normal of the hit, a base t value, and an ID to help the renderer know which type of object was hit. In addition, the ray class is defined by an origin and a direction, and it provides a function to determine the point along the ray for a given value of t. Now that we can test rays against objects, we need a way to generate those rays, one for each pixel. That's the job of the camera. First, we choose where the camera is in the world. This is the look from. Next, we choose where it's pointed. This is the look at. Finally, we decide which way is up. This is the v up vector. From these 3 vectors, we can construct 3 perpendicular directions. Forward, from the camera to the target. Right, horizontal direction perpendicular to forward and up, adjusted so it's perpendicular to both. We also set a vertical field of view, which controls how zoomed in the camera feels, and an aspect ratio to match our image's width and height. When we render pixel ij, we convert it into its normalized coordinates, uv, from 0 to 1. We then take the forward direction, add a horizontal offset proportional to U and add a vertical offset proportional to V. The result is the ray's direction, pointing from the camera's position through that pixel into the scene. Every pixel gets its own ray, and together they cover the entire image. Now we need to talk about the last critical element in our simple scene, the light. In the real world, light doesn't just appear out of nowhere, it has a source. In our renderer, that source is an area light. Instead of being a single point that sprays photons everywhere, an area light is a small, finite shape in space, usually a disk or a rectangle, that emits light uniformly from its surface. Why should we implement an area instead of a point? Because in the real world, lights have size, and that size creates soft shadows. The bigger the light, the blurrier the shadow's edges appear. In contrast, a point light makes razor-sharp shadows, which can look artificial. In code, we store our area light as a center point, two perpendicular vectors that span its surface, and a radius. These two vectors, let's call them U and V, are basically the local right and up directions for the light's face. They let us sample random points anywhere on the light's surface. Why random points? That's how we simulate the way light wraps around objects. Every time a pixel's ray hits something, we ask the light what a point on its surface looks like from that hit position. If we do this enough times per pixel, the noise averages out and we get realistic, soft lighting. The light is the last piece of a much larger structure that contains all of the information about our digital world. This is our scene class. Think of the scene as the boss of our little world. The scene class keeps track of everything inside the world and answers one simple but critical question. If I fire a ray into you, what does it hit? In code, the scene struct holds references to all the objects, our sphere, the infinite checkerboard plane, and the area light. It also stores the ambient light color and the gradient colors for the sky. The most important part is its hit function. This function takes a ray and checks it against every object in the scene. If multiple hits occur, it keeps only the closest one. This is how we make sure a wall in front of a sphere blocks our view of that sphere. It also has an occluded function, which is a stripped down version of hit. Instead of caring where a ray hits, it just says yes or no if something blocks the path. We use this when checking shadows. If the path from a point to the light is blocked, that point is in shadow. Finally, the scene has a sky function, which returns the background color when a ray misses everything. In our case, it's a smooth blend from white at the horizon to blue above. At this point, we actually have enough to piece together this simple render. Here's our sphere on top of our plane. Don't worry about how pixelated it is. This is just a result of scaling the image up. We can apply much better lighting techniques though, so let's implement them. Okay, now we'll make the lighting look convincing, but still keep the math simple. First, we create a scene with an area light. So far we've got rays hidden objects, but how do we turn a hit into a believable color? That's where the lighting function comes in. Let's break them down. First, the simplest. We add a small constant color everywhere called the ambient. It's like a faint glow that makes sure your shadows aren't pitch black. If the ray misses everything, we simply return the sky color. Now when a surface does get hit, and it can see the light, we compute diffuse light. Here, n.L means the dot product of the surface normal and the light direction. If they're aligned, it's 1. If it's perpendicular, it's 0. Negative values are clamped away. This encodes the basic idea. Light hits more strongly when it comes in head-on. On shiny surfaces, we add specular highlights, the bright sparkle. This uses the Blin-Fong model. H is the half vector between the view direction and the light direction. N.H measures how well the surface normal lines up with the half vector. Raising it to the shininess power makes the highlight sharp. Then multiply it by spec to scale its strength. Of course, the diffuse and specular terms only count if the light actually reaches the point, so before we add them in, we cast a shadow ray. Light intensity weakens as it spreads out in space. We model this with this line. Now for the cool part, reflections. Every time a ray hits a shiny surface, we compute a mirror direction. But real surfaces aren't perfect. To simulate glossiness, we sample a small cone around that ideal direction. The cone angle depends on the roughness of the material. A rough surface means a wider cone and a blurrier reflection. A smooth metal means a tight cone and crisp reflections. Finally, we don't just add reflections blindly. Reflections get strong at shallow viewing angles. Think of looking across water at sunset. We approximate this with the Fresnel slick function. So, putting it all together, the final color of the surface is ambient times base plus KD times diffuse plus specular plus KS times reflection, where KD is the diffuse weight and KS is the reflection weight via Fresnel slick. And that's it for this first step into ray tracing. This is my first ever video, so I'd really appreciate your feedback. If you found it interesting or helpful, let me know by liking, commenting, or sharing your thoughts below. Thanks for watching, and I'll see you in the next one.